Okay. So as I was talking about, the dipole moment could be of three types because it is something that we are relating with the symmetry and chirality. And dipole moment plays a very important role to understand the concept, like why we even talking about the molecule to be a chiral and how mathematically we can detect. We can't just have a molecule and if this is a pen and if it is made up of certain, all things are made up of certain chemical composition is there. So I can just see it and talk about it whether it is chiral or not. So there is something mathematically which we would be analyzing, which we would be quantifying, and on the basis of that we can say whether this particular molecule or the pen or something, anything like that, it is chiral or not. So when I was talking about the electric dipole moment, it is the distance between the two charges which are having the same magnitude of the charge, but the direction or the signs are different and they are having a certain difference. So your electrical dipole moment, which is given by mu E, it would be having a R into charge. So this would be a vector multiplication of your charge and distance. Similarly, if I am talking about the magnetic dipole moment, now instead of charge, that will depend upon the pole strength because we will be having a south or north pole into that. So they create distance is same, but now they're creating a pole strength. The magnetic pole strength is there. And in case of the quadrupole means four. That means four poles are there. So two positives and two negatives. So they will make a quadrupole. So corresponding to these three dipole moments, mu E is having highest strength compared to the mu M, and that quadrupole, it is very, very weak. So its contribution towards the dipole moment becomes even though negligible. So only these two factors, they remain the most prominent one when we are talking about the dipole moment factor. So first, as I said, for a transition to happen, it should be having a transition moment integral. And now this transition moment integral comprises of both the parts, both the electrical part also and the magnetic part also. So this formula would become now minus infinity to plus infinity. The psi is your wave function. Don't get confused. This psi with the ellipticity. This is your wave function of the excited state. Now this is your operator, that vector electrical dipole moment, and psi is your ground state and d tau is your volume element. And the second vector is minus infinity to plus infinity, excited state wave function, and mu m psi of ground state d tau. So these two dipole moments, they are very important. And also we know that electromagnetic radiation having both electric field and magnetic field perpendicular to each other. So because of this electric dipole moment, the molecule will tend to move in a linear fashion. So that will go to a linear fashion. Whereas because of this M, it will try to have a circular motion because we know that if we talk about the electric field, that's a static charge that does not move. But when we talk about the magnetic dipole moment, we are talking about the movable charges. So movable, but in a circular motion. So here, if this is we consider it as a plane. So we will be seeing that circular motion is happening. Now, for a molecule to be called as a chiral, these two things, these two moment or these two dipole moment vectors should be there or they should be active with that particular molecule. Say, for example, the molecule should move also, but its movement should be circular in nature. So if I have an A and this is a molecule and it is moving in this particular direction, but that motion has to be circular. So how it will go? It will go like this way. It is moving further, but it is going in a circular motion. Now this motion is nothing but your helical motion. Right? And we already know that wherever the helical motion is there, that will cause the chirality. Why chirality? Go back to the original definition of the chiral molecule. Chirality is something when there are two mirror images, they are non-superimposable with each other. And helical motion, if we'll say, this is my one direction. And if I have put the mirror over here, now this would be my other direction. And when you try to superimpose each other, they will not superimpose. So therefore, helical motion is chiral, And we saw that molecule having both the electric dipole moment as well as magnetic dipole moment, it is ultimately giving you a helical motion. Because of this helical motion, that particular molecule where both the vectors E and M, mu E and mu M, they are active, they are called as chiral. So is that clear?
Clear, ma'am.
Okay. So we understood that, okay, plane polarized light also was having a chiral helical motion. That's why we called it as a chiral. That is giving you a chiral environment. And the molecule also, when we are talking about, that is also having a helical motion. And because of that, we consider this to be a chiral molecule. Now, what are the conditions for this molecule to be a chiral? Hello.
Okay, ma'am, I am here.
Okay. So now we can just make few points that for that just to make ourselves more clear about this thing, that we were mainly talking about the light and matter interaction from which this whole course actually started. Now this light, we mean to have plane polarized light, and this matter is your molecule which we talk about the chiral. So for the plane polarized light, we understood it is having LCP and RCP. Depending upon different refractive index, it is giving us phi optical rotation. Depending upon different absorbance, it is giving us psi, which is ellipticity. Now for the molecule to be chiral or having the helical motion, we saw two factors are very important. One is mu E, another is mu M. Now, this is okay for the theoretical purpose, but how mathematically we'll be clear. Plane polarized is fine. We got the phi, we can quantify psi, that is fine. But how do we quantify mu E and mu N? That is not very easy because molecule is comprising of too many of electrons. And how do we quantify each and every mu E value and mu M value? So to make that easy, we need to understand that mu E we talk about that it would be having a linear motion. That means the distance, because it depends upon the distance, and distance is nothing but your XYZ coordinates. These are your translational coordinates, which defines the translation of your molecule, right? So if this is my coordinate system, this is Z, X, and Y. So this particular point, or here it is origin, so it would be 0, 0, 0. These coordinates would be 0, 0, 0 at the origin. And here, if my particle 1 is there, it would be having x1, y1, and z1. Okay, so because of this, we can define our mu E vector. So now it becomes even more easy. So if we need to see whether mu E is there, we need to see x, y, z vectors are active or not. Similarly, when we talk about the magnetic dipole moment, it actually relates with the rotational axis because it is only defining because of the rotation or the movable charges. So rotational axes are there, which are defined as Rx, Ry, and Rc. Along the all transitional axes, there would be rotation also. So they are defined as Rx, Ry, Rc. Now, so if in a molecule, we are saying that mu E and mu M both should be active for a chirality. So for that purpose, X and Rx, Y and Ry, Z and Rz, they all should be, these pairs should be having same symmetry. If they are same symmetry, that means they will be allowing us for the transition to happen for those two particular dipole moments to be active. So they can't be having different symmetry. So by different symmetry, it would be easy if I'll make you understand with a character table. So not much has been defined in the whole course about the character tables, because that would become even more difficult to understand, too much of character tables, but I will give you just a normal gist about it. So this is a character table is nothing but it combines all the elements, all the operations, and it will give you an order of your particular molecule. So in starting lectures, we understood that molecule can be classified whether it is linear, whether it is coming in a cubic point group symmetry, or it is dihedral, or it is a single axis. So that we understood, right? So if the molecule is having C2V point group, what could be the order of that? Do you remember? Like we actually talked about the order of C2V point group. How many order is nothing but the total number of elements that are present in the C2V point group. So what is the order of the C2V point group? Any idea?
Water, ma'am.
Yeah, water is example that I understood. Water is an example that is a molecule which is having the C2V point group. But I'm talking about the order. Order means how many possible symmetry elements are there which can give you an equivalent orientation. So is it having identity? Yes, it is having an identity. We saw that it is having C2 along the Z direction if I'm fixing it. We also saw that it was having sigma XY, sigma XZ, sorry, and sigma YZ. These are the two vertical planes. So this particular molecule, now not considering the molecule, I'm talking about a general term which is C2V. All the molecules which are having C2V point group, they all are having same character table. That's why the group theory makes our life very easy, because we have a numerous or infinite number of molecules. We cannot find out the point group for each and everything. If we know about one thing, then we can relate it with the other one. Say, for example, C2V comprises of all the molecules which are having these four elements. So these four elements are E, identity, C2Z. C2Z is nothing but rotation of the molecule to, with 180 degrees. Sigma V XZ, that means this is a plane along the X and Z direction, which is cutting your molecule into two halves, and sigma V YZ, which is bisecting your molecule into two halves. So is that clear? This is a kind of character table. In the first row, we would be having all the symmetry elements: E, C2Z, sigma V, XZ direction, and YZ direction. Is that clear? Because I'm trying,
Clear, ma'am.
yeah, I'm trying to explain a bit about the character table so that we should not directly jump to the conclusions. How do we get to know about the XYZ axis and the RX, RY, RZ? Now, if you will see along this was my first row, and this part was my, this is clear now. This is having my symmetry elements. Now at the left side, if you will see, these are called as Mulliken symbols. And these are nothing but the irreducible representations. So what happens to make our life more easy? There could be combinations of E, C2Z, sigma V, sigma XZ or YZ. So when we are drawing the character table, we need to define, okay, if my identity is 1. Say, for example, positive +1, minus +1, what it indicates. Positive +1, if it is not changing your equivalent orientation or direction of it. Say, if my molecule is as such, the H2O is there. If I applied identity, it will give me the same molecule. H1, H2, it is same because identity is there. It is not going to change anything. So for this, the +1 indicates, that means for E, after applying the E element, it is giving me same identical orientation. Is that clear now?
Clear, ma'am.
Okay. So now next part, if I am having C2Z rotation. Now, when I'm applying the C2Z, it is having, say, for example, how would I define it? Now it is changing its position. Even if it is equivalent, it is not identical. Say for example, we consider this as a -1. So the other one where after the C2 Z, if you are getting the identical one, that will give you a +1 sign. So maybe I can more explain with the model in the next lecture. But for this now, I would just define what are these signs. So these are the table. And here we have to make combinations in that way that the total order should be 4. So if I'll just combine the column wise 1 + 1 + 1 + 1, it is giving me 4. And we know that C2V order is 4. 4 is nothing but the total number of elements. And whatever the combinations that I'm taking, that should also give me the 1. Now, if you'll go to the row side, 1 + 1 + 1 + 1, it is giving me 4. Here also, we have to multiply it with that one. Like, it should be a square of it. Actually, it is square of it. So, it goes like, if I am having any element in the rows, so it will come to like this way, or if it is in column wise also, it has to be the squares of it. So when I'm talking about 4, what possible combination could be? So I can use 0, I can use 1, I can use 2. But I have to adjust the values in such a way, it should not repeat, and it should give me a square of sum of the squares equal to the order, that is 4. That is why first combination becomes all the particular columns are having 1, 1, 1. The first column is having 1, 1, 1. Now the second combination could be 1, 1 and 2 are negative. Now these two negatives could be at this position, and the other time, the last time, it could be like -1 here, -1 here. And if you will square them and add them, they will give you the 4 value, which is the order of your group. So these are the possible 4 combinations could be there when we are defining the character table. So is that clear? I know that is a bit difficult to understand, but I will make it easy maybe in the next session where I will be defining more examples. So by this time you understood that why we are taking these 4 combinations only. Why are we not taking 1, 0, 2 square or something like that?
Okay, ma'am, I can understand.
Okay. So for example, if you will say that we know max 2 square equals to 4, right? So this could also give me a value, but keeping all the values as 0, 0, 0 and keeping only 2 there, that doesn't make any sense, because this +1, -1 that defines whether it is giving you the same molecule or it is giving you a different equivalent configuration of it. So we got the 4 combinations. Now our main active mode, like main perspective of this particular character table understanding is that we need to see this A1, A2, B1, B2, and these things. As you can see, I was talking about the mu E and mu M, that electric dipole moment and the magnetic dipole moment. The electric dipole moment was having X, Y, Z. So here is your X, here is your Y, and here is your Z. And Rx, Ry, Rz. So these vectors are there, and you do not have to memorize it. It is, suppose it would be given in the exam if they are asking. So now we need to see that X, Rx should be in one group, Y, Ry should be in one group, one symmetry there. They should be having same symmetry, and Z, Rz should be having same symmetry. Now, what you're seeing on the left side, this one, A1, A2, B1, B2, they are nothing but called as irreducible representations. A1, A2, B1, B2, these are nothing but your irreducible. That means those representations which you cannot reduce any further. Say, for example, if I have 4 and 4 can be cut down to 2. 2 ka square is 4, or 1 + 1 + 2, that is 4. So that means one number can be further reduced to some other numbers. But if I'm taking 1, so 1 can't be further broken into any other number. So this is the way you can understand what is reducible, what is irreducible. 4 can be reduced to some other numbers, but 1 can't be. Now, how do we define this A1, A2, B1, B2? So if I have a one-dimensional representation, only one dimension is there. So that would be when beneath my C2Z, or if you will see the identity column, it would be having only 1, 1, 1, 1. So that will give you A or B. So these symbols come under when I am having beneath my identity column, I'm having only 1, 1, 1. So that could be giving representation as A or B. Now, if under the principal axis of rotation, that C to Z in case of C to V, if it is +1, then it is A representation. If it is -1, then it is B. So as you can see over here. So beneath the identity column, all are 1, 1, 1. So that means either it can take A representation or B representation. But among them, which one is A, which one is B, we can only be defining it when we see the C to Z. Now see the symbol. It is +1, that's where the symbol is A. It is +1, that's where the symbol is A. Here it is -1, it's B, -1, B. Up to this point, it is clear? Then how we came to A or B and how do we define A and B?
Ma'am, once again, you will explain the 1, 1, -1.
Okay. So like representation or how do we take this combination? The symbols you're talking about, or do I need to define why I took 1, 1, 1, 1, 1, 1, -1, -1?
Ma'am?
Hello?
Ma'am, what, ma'am?
I'm asking like what you want me to explain, whether how I got this A, B, or do I need to explain how I am making the character table 1, 1, -1, -1?
Okay, ma'am, I can understand. +1 means A, -1 means B.
Yeah.
But
how are we taking that? That is what your question. Why are we taking this +1, -1?
yes, ma'am. Yes, ma'am.
Okay. So what happens is, just we are talking about the mathematical thing. So if I'm having this C to V, this is clear that you are having order as 4. Order is nothing but the total number of symmetry elements. It is having E, C to Z, 2 sigmas. That is clear? Okay. So is this clear that why C2V we are considering? We need to draw a character table, and C2V that it is having an order of 4. That is clear?
Clear, ma'am.
Okay. So for defining the character table, to make that character table, we need to define some numbers which can form that character table. So what could be, these are called as dimensions. So what would be the dimensions? The dimensions are being defined as L. So what should be the dimensions or Li? Say for example, the square of it, that should give you 4. Right? So this whole sum, the dimensions that I'm putting into the whole, each and every block, that sum of all the dimensions should be giving me of total value of 4. Say for example, if I have L1 square plus L2 square, L3 square plus L4 square, that should come as 4. What could be the possible combination over there? What values you can do? You can either take 0, you can either take 1, you can either take 2, or -1 also, right? So if I am putting the first and simple case, I put L1 equals to L2 plus L3 equals to L4, that is 1 plus square, 1 square plus 1 square plus 1 square. This is giving me 1 plus 1 plus 1 plus 1, that is 4. Is calculation correct?
Correct, ma'am.
Okay. So if I am having this one, the other possibility could be so now we got to know that only one we are taking. If I'm taking other than that one, it is not going to define because we can't take here 0 or 2. If I'm taking 2 for that matter, other things would become 0 and 0. Is that clear? Like a dimension of it would become 0 if I'm taking that into consideration. So in that particular case, the dimension of any particular representation can't be 0. Is that clear? Is that true? For example, here. So if I'm taking an identity, if I'm taking this 1, this is 1, this is 1, And now out of these 1, 1, what could be the possible combination? So firstly, I gave all of them as 1. That squares became 4. Now I will choose 2 as plus 1. And also actually this mathematical or making of the character table is bit tricky because we have to follow up all the steps, how to put first column, then we have to do the second column. Now, if I have to say, for example, I made this first row as 1, 1, 1. Okay, this is filled. And this is also filled. Because these sums are equal to 4 and these are equal to 4. Now I have to put the values in such a way that the squares of it should give me 4, and multiplying 2 rows should be giving me a value of 0. For example, if I will put like this way, if you will say, ma'am, what happens if I am putting, because this is fixed now, we have fixed this as 1, and next I am taking as -1 plus square, then -1 square, then -1 square. Again, it is going to give me 4. Is that true? Because square of negative is also positive.
Ma'am, here in column wise,
Yeah.
1, 1, 1, 1, 4. Okay. If we are going to multiply in row wise means
Row means like, say, first question of yours should be like, why I have put all the positive values over here? Because when I'm talking about the dimensions, I need to talk about the dimension of my particular representation. That can't be negative, that can't be 0. Is that true?
yes, ma'am.
Okay.
True.
So now we have to make certain combination which is going to give me an order value of 4. So I got like, okay, if I have 1, 1, 1 in each of them, that would be 4. That is clear. Now this is your row 1 along this horizontal. This one is your row 2. This one is your row 3. This is your row 4. Now I'm saying what x, y, z value should I put? This x, y or ABC for that matter if I will take. So what should be the A, B, C, D, E, F, G, H, I? I don't know about these values. Now I need to know one combination I've written 1 square plus 1 square plus 1 square plus 1 square, that is 4. Now what should be the A, B, C value, D, E, F value and G, H, I value, so that their squares and addition of those squares should give you 4. And if I try to multiply this one row to the second, that means 1 into 1 plus 1 into A plus 1 into B plus 1 into C, that should be 0. That means these two rows or any two rows for that matter, they should be orthogonal to each other. They should not be having any value other than 0. So what should be the combination of such? And if I'm adding, after multiplication, if I'm adding those two rows, that should give me a value of 0. This should hold true for all the combinations. That is why if you will, for today only, you just go back and try this, find out the A, B, C, D, E, F and G, H, I combination by yourself. We will just look at this one for now. So maybe in the next live session, I will take up 2, 3 more examples to make you guys understand about the character table. So here, if you see, okay, so the first table is fixed. 1 second. Okay, so here we fixed this one, we fixed this one. A, this is clear. This one, this column is clear. Forget about A1, A2, B1, B2. We need to name them. So consider them as row 1, row 2, row 3, row 4. We don't know the representation. We need to give the representation. And also we fix this one row we have filled it. Row 1 is full. Okay, row 1 is nothing but your 1, 1, 1, 1. Now row 2, if I'm taking 1, I'm taking this from the above. 1, minus 1, minus 1. Now multiply each column ka thing and then add on. So it would become 1 into 1 plus this 1 into 1 plus now this 1 into minus 1 plus 1 into minus 1. Now add on. And tell me the value, what would be the value of it? So 1 into 1 will give you 1 into 1 is
1,
plus 1 into 1 is
1,
then 1 into minus 1 is,
minus 1,
and next one is also minus 1. Now add on, and what
Nice.
would be the value? 1 plus 1 is 2. Minus 1 is minus 2.
0.
2 minus 2 is 0. So we got to know, okay, R1 into R2 combination, even though if I will square these values, 1 square plus 1 square minus 1 square and minus 1 square, after adding this value alone, independently, if I am adding and squaring those things, it is 4. But if I'm taking two combinations of row 1 and row 2 and then I'm multiplying and adding, that is giving me 0 values. That means R1 and R2 are orthogonal and this combination is fine. Similarly, it should happen with other rows combination also. Now take this one. Now this was minus 1, and here now the minus 1 position has been different. This minus 1 has gone to this one. Now 1 into 1 plus 1 into 1 is 1. 1 into minus 1 is minus 1. This 1 and minus 1 will cancel out. That is 0. Now this is minus 1. Minus 1 into 1 is minus 1. And minus 1 into minus 1 is plus 1. So this minus and this plus will cancel out again. Two rows, R2 and R3 will again be a 0. And if you will just square and add these things, 1 square is 1. Plus minus 1 square, that is 1. Plus 1 square plus minus 1 square is 1. So adding all the squares of these 1 and minus 1, that will give you 4. So this addition is again coming as 4. And if I'm multiplying R2 and R3, that is giving me value of 0. Similarly, if you will multiply R1 with the R3, because R1 is all 1, 1, 1. If you multiply it with 1 into minus 1, 1 minus 1 plus 1 minus 1, that is giving you 0. So any combination of two rows, any two rows, if you multiply, add and multiply, that is going to give you 0. That are called as orthogonal rows. And when you are squaring these individual values, whatever the element in each of that value is coming, if you're squaring and adding them, that is giving you order of the group. That means these values are right. So now you understand that how we are combining that 1 and minus 1, not other than these 1 and minus 1, we are not taking any other value. Is that clear? We're not taking any other possible combination also.
Okay, ma'am. Clear.
So maybe in the next live session, I will take 2 or 3 more character tables that there we will define and we will formulate each and every step, because this is a bit more lengthy and we won't be able to cover it in next 30 to 45 minutes. The main take home message right now is not to understand the character table. The main point that I wanted to highlight, that look at, and depending upon that, the main point that we were talking about, as I said, when the dimension under that value under the E, that identity element is 1, that will give you A or B. That is the sign of the representation. Okay. Now, whether it is A1, whether it is A or B, 1 is for A and B both. Whether it is A or B, that will come from your C to Z. This is your principal axis. If it is plus 1, then it is A. If it is minus 1, that is B. Now you can see here. If you will see here, this is 1. That is why it is A. This is 1. This is A. Minus 1 B. Minus 1 B. Is that clear now?
Clear, ma'am.
Okay. Now, if you see the representations clearly, it is A1, A2, B1, B2. Now, from where this subscript 1 and 2 is coming, take this one plane of reflection. So if you are taking one plane of reflection compared to that other one, you have to ignore. If you are taking the second plane of reflection, depending upon that, your values will be different. So if I'm taking this sigma V Z, now for 1, it is giving me 1. And if it is minus 1, it is giving me 2. So this plane of reflection, any plane of reflection will give you, for plus 1, it is 1 symbol, minus 1, it is 2. So that is why if this is 1, this becomes A1. This is minus 1, this becomes A2. This is plus 1, this is B1, minus 1 and B2. Is that clear now? This has defined our representations, all the representation now. Is there any doubt?
No doubt, ma'am.
Okay. Say for example, if I am considering this sigma V Y Z as my main plane of reflection, and corresponding to that, this would remain as A1, this would become as A2, this will go as B2, and this will become as B1. Is that true? Because this is -1, this is +1. So even if they are exchanging their places, that is not going to affect more, because these are just the representations. Corresponding to that, your all the things would be changed accordingly. So even if you are taking the second plane of reflection as depending upon that, you're defining your representation, that is also fine. So it is not like the number or the representations should come like A1, A2, B1, B2. How are they coming, and with respect to that, with what you are taking, that is not a problem. So now this particular point is also clear how we got the representation. Now our main factor was from where we started. Actually, we were interested, as I said, that we need to see this was my part of the electric dipole moment. This is the rotation one is a part of magnetic dipole moment. So these pairs in the same direction, Z and Z are in the same direction, Y and Y in the same direction, and X and X is the same direction. So these should be lying, or they should be having same representation of the symmetry. So if you will see, Z is having A1, whereas RZ is having A2. So that means Z and RZ, they are not belonging to the same group or same representation. Here, if you will see, the combination is there, X and RY, but X and RXs are still indifferent. So when they are not having the same symmetry, they are not having mu E and mu M active. They are inactive. Therefore, C2V is achiral. We already knew this fact that only the CN and DN point groups are the chiral point groups. Only those molecules which are having CN and DN, they are not having any sigma, they are not having any inversion center, they are not having any improper axis of rotation. They would only be considered as a chiral molecule. But how the mathematically it is possible? Only looking at these factors, we got to know that mu E and mu M, that both dipole moment vectors XYZ and RX, RY, RZ, if they're not lying, the pair is not having the same symmetry transformation or the representation, they can't be active. That's why the C2V molecule, the molecule having the C2V representation, that can't be chiral anymore. Is that clear?
Clear, ma'am.
Because we started with this general statement of CN and DN in the first or second week of lecture, but now we are coming with the proper explanation and the mathematical version of it. How do we define it based on the dipole moment which actually takes place in the transition? Now, if you will consider here, we will take a case of character table of a chiral molecule. Now, okay. So now this one is the character table of C3 point group. C3 is having total order equals to 6. Okay. Now if we'll calculate 1 square plus 1 square plus 2 square, 1 square plus 1 square plus 2 square. Is it coming as 6? This is defining properly?
Yes, ma'am.
Yeah. So here also, if you will see along the row wise, you have to now multiply these coefficients also, because they are 2 in number. Either you can segregate them, or if you're counting, so you have to multiply with them. That means there are 3 types of C2 prime, so that we have to count. So now if I'll multiply here, 1, the coefficient, into 1, 2 into 1, 3 into 1. These are the squares. It will become 1 plus 2 plus 3, that is also 6. If I'll take the other part, this one,